Hi class, we are now on 12.5, measuring acid and base concentrations. So we're going to look at pH indicators first. So chemists often need to determine the pH of an aqueous solution. One way of doing this is with pH indicators. These are compounds, that change color depending on the pH of the solution. The color changes indicate the approximate pH of the solution. One of the oldest and most common indicators is litmus paper is what they call it. Litmus paper turns red in the presence of an acid, but blue in the presence of a base. Chemists sometimes test for acids or bases using litmus paper. Small strips of paper that are pre-treated with litmus. I've only known of litmus paper. I've never heard anything referred to just as litmus, so take it as you will. The paper comes in red or blue and changes or retains its color depending on the pH. A slightly more advanced form of litmus paper is pH paper. This paper contains a blend of indicators and produces a series of colors ranging from deep red to deep blue. pH paper allows us to approximate the pH to the nearest integer. So how this works is that you would have a red litmus paper, and it's red as it's dry. If you stick it into a solution that's basic, it will turn blue, which kind of looks purple, to be honest with you. And if it's acidic, then the red paper stays red. It doesn't change. But if you have, and this one doesn't show it, there's also blue paper that looks like this when it's dry. If it goes into, so the blue paper goes into a basic solution, it stays blue. But if it goes into an acidic solution, then it changes red. So you have litmus paper that's red, that stands for acidic, and you can test in basic solutions, it'll turn blue. And then you have blue paper that you can test for acidic conditions, and it'll change to red or kind of a purple if it is, but it'll stay blue in basic solution. Then you have pH paper that you can stick this paper in, and it will change color to the pH scale. So you dip it in, you wait about a minute, 30 seconds, and then you compare it, and you can see what color it is, what pH it is based on this color. So this color here, if we take it, it's about a pH 6, because it's not a 4 and it's definitely not an 8. They have other ones that expand to all of them. It's 1, 2, 3, 4, 5, 6. It goes through all of it. So they're more specific. Okay, a third common indicator is a compound called phenolphthalein. In acidic solution, phenolphthalein is colorless. In basic solution, it turns pink. And when we do titrations, you want it to be a pale pink because you want it close to, as neutral. I don't want to go too much into it right now, but neutralization of the base and the acid. So it's equal amounts. And if it's dark pink, then it starts going into a basic solution. So again, it's acidic. If it's in acidic conditions, it's colorless because it's an acid. It's a weak acid. And then as more base is added and it starts getting to a pH of a little bit past 7, closer to 8, then it turns pale pink. And if you go past it, then it goes into a bright pink. For more precise pH measurements, chemists use an analytical instrument called a pH meter. That's exactly what it sounds like. They stick this probe into a solution and it'll read what the pH is on it. In the laboratory, chemists commonly use an analytical technique called titration to precisely measure the concentration of an acid or base. For example, if a chemist wishes to determine the concentration of a solution of hydrochloric acid, we would follow these procedures. We prepare a base, a basic solution, something like sodium hydroxide with a known concentration. So we could say that it would be like, for instance, 1 molar sodium hydroxide. 2, we precisely measure a small volume of acid. So this is going to be the acid right here. Place the acid in an Erlenmeyer flask, and we make sure to add 1 to 2 drops of the phenolphthalein. That's all you need is 1 to 2 drops of the indicator here into the solution. This indicator, because you put it into an acidic solution, it stays colorless. But once it meets the equivalence point of the base, meaning equal moles have canceled out and neutralized, then it should turn pink. We fill the beret with the known basic solution. So you can't see the beret here, but it's here with base in it. And then we add the base into, and you can see it's a little bit bright pink right here. When that solution turns all pink and stays pink, then we've hit the amount that we need. So a beret is a small dispensing tube with volume markings. We measure the initial volume. So when we fill the solution in, we know what the initial amount is. And then what the final amount is, once the solution is turned pink, we can read it, and that's going to be a final minus initial, and that will be the volume that we've used. So we add the base to the acid, swirling the Erlenmeyer flask, occasionally to mix the solutions. As more base is added, a pink color will begin to form and then disappear. As you're swirling it, it'll mix. Slowly add base, drop by drop, until a faint pink remains. The one thing that I don't like about these pictures is that I always tell my students, don't do this on a black countertop. Always have a white piece of paper underneath, because the black will not allow you to see the pink very well. And you're probably past what you think it is because it's not showing in contrast as well as having a white piece of paper underneath. I apologize, you can hear my cat. She likes to sing. Okay, so by adding the solution slowly until the faintest pink color remains, the chemist adds just enough base to neutralize the acid. So remember, this is why it's a neutralization reaction, because it produces water and a salt. There should be no more base, there should be no more acid left over. For example, above, the neutralization reaction of HCl with sodium hydroxide produces salt and water. In this reaction, 1 mole of HCl reacts with 1 mole of sodium hydroxide. Therefore, the chemist has combined the same number of moles of acid and base in the solution, enough to equally cancel out. Since the molarity, moles over liter, times the volume equals the moles, we can, excuse me, I lost my place. We can rewrite this equation as MAVA equals MBVB, where MA and VA are the molarity and volume of the acid, and MB and VB are the molarity and volume of the base. And if you do this right, what they're saying is that this is moles over liters, this is liters. So liters and liters will cancel out, leaving the moles. That's where you see it up here. In a titration, we measure the volume of the known, the molarity of the known, and the volume of the unknown. We use this information to determine the unknown concentration. So let's look at an example. Excuse me, a 25 milliliter sample of HCl is neutralized by a reaction with 17.4 mils of 2 molar sodium hydroxide. What was the concentration of HCl in the unknown sample? At the neutralization point, the number of moles of acid are equal to the number of moles of base. So that's what you're seeing here. That means it's neutralized out. Therefore, we can say that MAVA equals MBVB. We know the values of VA is 25 mils, and VB is 17.4, and MB is 2 molar. We're trying to solve for the molarity of the acid. We therefore rearrange the equation. So we rearrange it to solve for the one that we don't know. And this is equal to 2 molar times 17.4 mils over 25 mils. So if we cancel out, it gives us the molar of the hydroxide, and the HCl, which is our unknown molarity, and that is 1.39 molar. So notice that because the volumes of the acid and the base cancel out, it's not necessarily to convert from milliliters to liters. Sometimes we need to do titrations for reactions in which the coefficients of acids and bases are not equal. For example, consider the neutralization of barium hydroxide with hydrochloric acid. Based on the balanced equation, the neutralization reaction requires twice as many moles of HCl as barium hydroxide. So we cannot use the simple assumption that the moles of acid and moles of base are equal, as we did above. So what can we do? In order to set the moles of each reactant equal, we can divide by the coefficient of each reactant in the balanced equation. The moles of acid over the coefficient of the acid equal the moles of base over the coefficient of the base. Because moles equals MV, we can say that MAVA over CA, where Ca and Cb are the coefficients of the acids and the base in the balanced equation. Notice that if Ca and Cb are 1, this simplifies the relationship above for a 1-to-1 acid to base ratio. So this is being taught a little different than what I know or how I do it. In my examples, I'm going to show you how I do it. I'm sure this is simplifying it, and if I was learning it, this might make sense to me, but because I'll be honest, because I didn't learn it this way, it's a little confusing. So, but I'm going to present the way they want me to teach it to you. Okay, and it might actually end up being the same, I just don't like the way it's explained. All right, so a chemist needs to completely neutralize a 0.600 liter of a 3 molar aqueous sulfuric acid solution. What volume of 0.80 molar aqueous potassium hydroxide is necessary to do this? If the chemist adds 5 liters of the aqueous potassium hydroxide to the solution, will the resulting solution be acidic, basic, or neutral? Again, let's begin by writing a balanced equation for the neutralization reaction. I always suggest writing a balanced equation out because you never know how many moles just by looking at stuff. Things can be really deceiving. So we first find the moles of sulfuric acid. So we have, sorry, I just realized I read the wrong problem. Okay, so let me make sure I am reading this right. A 30 ml sample of barium hydroxide is neutralized with HCl solution having a concentration of 0.400 molar. If 22.6 mils of aqueous HCl are required to complete the neutralization, what is the concentration of the barium hydroxide solution? So again, make sure you write the balanced equation out. So we're given the volume, the concentration of the acid, and we're asked to find the concentration of the base. Our strategy is similar to the previous example, except that we start with the acid and find the base. So we use the molarity and volume of HCl, and we find the moles of HCl, which is the 0.400 moles right here, because the molarity, which is moles over liter, and the volume are going to cancel out, leaving us the moles. Okay, so when the liters cancel out, this gives us 0.00904 moles of HCl. Next, we convert to moles of base. We use 0.00904 moles of HCl. From the balanced equation, we use 1 mole of barium hydroxide per 2 moles of HCl. The moles of HCl cancel out, and giving an answer of 0.00452 barium hydroxide. Finally, we use the moles of barium hydroxide and the volume of the base solution to find the concentration of the solution. And that gives us an answer of 0.151 molar barium hydroxide. So this page to me is a little confusing, but this is exactly the way I do it. So the way they're explaining it to me is on this slide I didn't like, but these are exactly the steps in order to do this. Okay, so now let me read the one that I had already read. A chemist needs to completely neutralize 0.600 liter of a 3 molar aqueous sulfuric acid solution. What volume of 0.80 molar aqueous potassium hydroxide is necessary to do this? If the chemist adds 5 liters of the aqueous potassium hydroxide to the acid solution, will the resulting solution be acidic, basic, or neutral? So in this case, again, write a balanced equation out. We first find the moles of sulfuric acid, which is 3 moles per liter, times 0.600 liters, which gives us 1.8 moles of sulfuric acid. We can relate this to the moles of base. 1.8 moles of sulfuric acid times 2 moles of potassium hydroxide per mole of sulfuric acid. So we're right here looking at this. And then from there, the last step is to use the molarity of the potassium hydroxide solution to convert from moles to volume. The potassium hydroxide solution is 0.80 molar, which means 1 liter of solution contains 0.80 moles of potassium hydroxide. We write this as a conversion factor with the moles in the denominator, which means on the bottom, and the moles of potassium hydroxide cancel, giving us an answer of 4.5 liters of solution. The second part of the question asks whether the solution will be acidic, basic, or neutral if 5 liters of aqueous solution, potassium hydroxide are added. Since only 4.5 liters of the basic solution are needed to neutralize the acid, if the chemist adds 5 liters of base, the base will be the excess reagent, and then the final solution will be basic because there will be a portion left over. Okay, so let's take a look at some problems. A chemist titrates a solution of nitric acid. She finds that 23.4 mils of 1.05 molar sodium hydroxide are required to neutralize 25 mils of the acid. What was the molarity of the original nitric acid solution? So this is how I do it. It's not really different than what is being given to you, but I write a balanced equation out, and then I pull the information above and I write it directly underneath. So I can see what I have and I can see what I'm missing. So I'm missing a molarity here, but I have this information. I have a volume and I have a moles. This is going to give me moles per liter, sorry. The volumes are going to cancel out and give me the moles. So here we go. We take the oh, I didn't do this right. I apologize. I half-assed this. I didn't realize I messed this up. This is liters because this is 23.4. I'll fix the actual PowerPoint slides though. This should be liters, so remove the M, and there should be a liter underneath here. So the liters cancel out, and that gives me 0.02457 moles of sodium hydroxide. I'm going to then take that, and I'm going to do a ratio, which is really 1-to-1. So it ends up being that I have the same amount of moles for the nitric acid. I then take, see, my cat likes to sing. She steals my socks and then walks around with them in her mouth singing. I don't know why. So 0.0, so then we take the moles of nitric acid and the volume that we know we have, and that gives us moles over liters, which gives us the molarity. So acid-base titrations with different coefficients. So this is just a step-by-step of how you should handle it. There's only maybe one extra step or two when instead of doing a 1-to-1, but that's really not very different, and you shouldn't panic when you see when there's different coefficients. So what volume of 0.100 molar HCl is needed to neutralize 25 mils of 0.100 molar barium hydroxide solution? So again, I put out a balanced equation and I put the information I have. So this is what I forgot to do on the other one. So I take this to liters, I take the molarity, and now what I do is I have a coefficient that's not 1-to-1. So I have 1 mole of barium hydroxide, but I have 2 moles of HCl. This gives me 0.005 moles of HCl. I'm now going to take that with the volume, with the molarity of HCl. If I set this up, then that means that this is going to flip, and liters will be on top, moles will be on the bottom, and that's going to cancel out the moles and leave me with 0.00 liters, which is 50 mils. It takes 50 mils of a 0.200 molar sodium hydroxide to titrate 50 mils of sulfuric acid solution. What is the concentration of the sulfuric acid solution? Again, I set it all up. And if you notice, the steps aren't changing. It doesn't matter if you're working with a base or an acid. The steps do not change. It only changes depending on if it's asking for molarity or if it's asking for volume on the last part, really. But you need to get moles, and you need to consider the coefficients. And if you do all that, you should notice the steps are usually the same. If it's not, then there might be something wrong. So in this case, I take the volume. So you take the one that you have the volume and the molarity. So that cancels these out. It gives me sulfuric acid, but it's a 2-to-1 ratio. So I have, oh, I messed this up. I just realized right now this should be on top and this should be on the bottom. I apologize. I'm human. Sometimes I work on these all night and I don't catch some of the stuff I do. But it gives me, basically I calculated it right. I just didn't enter it here right. So it's giving me 0.005 moles of sulfuric acid. I plug that in with the volume, and that gives me 0.00 molar of, and which is matching B. So the answer is right. I just didn't set this up right. The pH of a 0.25 molar sodium hydroxide solution is tested with a piece of litmus paper. What color will the litmus paper be? Okay, so first let's understand this. The pH of a 0.250 molar sodium hydroxide is tested. Sodium hydroxide is a strong acid, base. It ionizes completely. So it's really high on the pH scale. So if it is, then we expect if you're using litmus paper that is red, it's going to turn blue, which is what the picture's showing. And that's exactly what happens. A few drops of phenolphthalein are added to a beaker containing 25 mils of 0.10 molar sulfuric acid solution. What color will the solution be? So if you're getting ready for a titration, you want phenolphthalein in. Sulfuric acid is an acid, and it doesn't matter if it's a weak acid or a strong acid, it's an acid. And when you're adding phenolphthalein to it, then you expect the color to be clear because you're putting an acid in an acid. It only reacts when it starts dealing with the base. That's when the color changes, and it's a pH indicator. So what happens is that the pH is low, and as more base is added, the pH is going up, up, up. Let's say it starts at 2, goes to 3, goes to 4. The more base is added till it gets past 7, and it's almost to 8, the color changes. A solution has a pH of 3. When electrodes connected to a light bulb are placed in the solution, the bulb glows dimly. The solution must be. So before we even look at what we're given to, let's understand what's being asked here. We have a pH of 3. pH of 3 is below 6, so we have a weak acid, almost a strong acid, but more a little weak. Why do I know it's a weak acid? Because it's dimly lit. That is telling you right here, the bulb glows dimly. If it's a strong acid, the ions allow the electrical current to go through very strongly, and this is very brightly lit. So because it's weakly lit, it's only got a few ions in it to allow an electrical current. Now, if it's in a pH of 3, it's acidic. So we're looking for a weak acid. So potassium hydroxide's out. That's a strong base. We don't care. I'm going to skip this one. Nitric acid is an acid, yes, but it's a strong acid. The bulb would grow very bright. NaCl is a salt. We don't care about that right now. And this is a weak acid, a base. So the only one that we have here is acetic acid, and acetic acid is a weak acid, which is only going to allow a dimly lit bulb because there's only very few ion. When placed in solution, it ionizes only to a very small percent, and it's those ions that are allowing that current to glow dimly.